With our first example, we were given something in vertex form, which I've reminded you looks something like this. F of x equals a constant, non-zero, times x minus h squared plus k. And we were able to graph things fairly nicely because we could just pick out the vertex. We were able to see whether it opened up or down by whether a was positive or negative, all of that good stuff. Okay. Here, I'm given a quadratic function in standard form. Some x squareds plus some x's plus a number is equal to my f of x. So I'm asked to first of all do something called completing the square to get it into this vertex form, and then once it's in that form, we'll go ahead and graph it. Okay. Now, for completing the square, it's helpful to remember what a perfect square looks like. I'm going to write out what x plus a number that I'm calling d squared looks like. Okay. I'm using d here because this would be my a x squared plus b x plus c. D is just the next number. There's nothing important about that except that I'm not using it for anything else. I will point out what shows up in vertex form is x minus a number squared. But we've seen that if I have something like x plus 2, that's the same as x minus negative 2. I find it easier when I'm doing the work of completing the square to work with x plus a number. Sometimes that number will end up being a negative number, and then this will look like a subtraction problem. But I'm going to write it as x plus d squared. So essentially, what we're saying here is that what I'm calling d is going to end up being the opposite of h. If I'm adding d, and that's the same as subtracting h, they would just be opposites. Okay. But x plus d squared, a perfect square of a binomial, would be x plus d times x plus d. It is not just x squared plus d squared because exponents do not distribute over addition. But I could FOIL this out, and that would be x squared. Outsides and insides each give me a copy of dx, so that's plus 2 copies of d times x. Plus the last terms would give me a d squared. Okay, so I'm going to be taking advantage of this formula here in trying to just rearrange the right-hand side here. Now, I did mention that when things are in standard form, so that we say the coefficient in front of x squared, we're calling that a, that's the same a we're going to see in vertex form. So this is kind of a nice case where my a, the coefficient in front of x squared, is just 1. So I don't really need to worry myself about that too much. Okay. The next example we do, we'll take a look at where I've got a coefficient other than 1. But basically what I want to do is I can see that in this formula for a perfect square, I'm getting 1 copy of x squared, I'm getting some x's, and I'm getting a number. Okay. Over here, I have 1 copy of x squared, I have some x's, and I have a number, but I think it's probably not the number I'm looking for. So I'm just going to leave some space, and then I write that I've got a plus 6 here. I'm hoping that these first 2 terms, the x squareds and the x's, are going to match the first 2 terms of my formula here. So I need to have 1 copy of x squared, and I do. The number of x's that I have is supposed to be 2d. But if I look here, the number of x's that I have is 4. Well, if I set those equal to each other, I can solve for d. Oops. Yes, d would simply be 2. With that choice for d, these first 2 terms match my formula for a perfect square. But of course, once I know what d is, d squared would just become 2 squared, which would be 4. So the number that I want to be adding to this is 4. Well, that's not the number that I had. But what I can do is I can say, let's add 4 and subtract 4. That way, all I'm doing is adding 0, which doesn't change a thing. But then I can group things. I can say now with this 4, this x squared plus 4x plus 4 matches the formula for a perfect square. And then I'm adding to that a negative 4 plus 6. So this negative 4 that I also had to introduce in order to be able to add the 4, I'll just combine that with the 6 that I already had. Then I can say now that's x plus 2 squared. Now we are going to spend a lot of time this semester factoring. This is some of the easiest factoring you'll ever do. If you've just completed the square to match this formula, these terms are going to factor into x plus d quantity squared. And then this would become plus 2. Now, all of this was just equal to f of x, so my vertex form we've now got. F of x is equal to x plus 2 squared plus 2. Excellent. So let's graph that. Now, I can pick out what the vertex is from here. I'm adding 2 to x. That's the same as subtracting a negative 2. So the x value of the vertex would be a negative 2. And then we add 2 after we square, so the y value of the vertex is 2. So there's my vertex right there. Okay. Now, I can tell this one's going to open up because my a, the number that I'm multiplying by, is just 1, positive 1, so we're not doing a vertical flip. So it's like my parent parabola, which opens up. Okay, so I was asked to graph this, including the vertex, which I graphed, and the intercepts. If this opens up, I'm not going to bother trying to find the x-intercepts because there aren't going to be any. Okay. So I'm just going to find the y-intercept. That's going to give me a second point, and I'm just going to use that to determine how steep things should be. Okay. So the y-intercept is on the y-axis, so the x value will be 0. If I plug in 0 for x, I'm going to get 0 plus 2 squared plus 2. That's 2 squared plus 2. That's 4 plus 2. That's 6. So the y-intercept is 0, 1, 2, 3, 4, is the point. Make sure you label it as a point, not just a number. It's the point 0, 6. And that does the nice job of telling me how steep to make this. Basically, since since our a was 1, this is the same width as our basic parent function would be. We haven't stretched it or shrunk it at all. Excellent. So we've got that graph. I'm going to just ask a couple more questions about this. We said we can talk about domains and ranges. Let's do that. And then let's also find the intervals on which this is increasing and decreasing. So my domain, negative infinity to infinity. That's true for every quadratic function. I can plug in anything I want. My range, well, here the vertex is a low point. So my range is all the y values from the y value here, which is 2, on up. So that would be 2 to infinity. And then if I look for the intervals of increase and decrease, I can see we start going down, then we end up going up. Remember, those intervals that describe the behavior, we're going to describe in terms of our x values. Because the y values I hit on this section of the graph where I'm coming down are exactly the same as the y values I hit when I turn around and start going back up. But if I look at the x values, until we hit the vertex, which has an x value of negative 2, we're decreasing. So I could say we're decreasing from negative infinity to negative 2. And remember, we can include that finite endpoint in our answer. And then we're increasing from negative 2 to infinity. All right, so that was an example of having to complete the square. This was kind of a nice example because our a was 1. In the next video, we'll take a look at what if a is not 1. That's a little bit more complicated.